Well, so I feel very strange because I woke up at 3:30 this morning to go from countryside of France to here, so I really feel jet lagged. So I hope you don't feel the same, and at least I'll be able to be on time. So please help me because I tend to be a little bit chatty. For those who do not know, Linaro is the ARM ecosystem collaboration. So we have companies like Google, Facebook, Alibaba, Red Hat, Cisco, Ericsson, Huawei, Nokia, Cavium, NXP, TI, ST, well, I stop. So many of those companies are either building silicon or building systems on top of that, and we collaborate inside Linaro to produce things and to push technology in many different communities. And out of the members, there was a request to have a technology to sustain time-sensitive networking. We tried to do it with the kernel, with 500 megahertz, 1 gigahertz CPUs, and the result is that the latencies or jitter are not really consistent with what the applications want. And when the latency is between 20 and 40 times what it should be, and when the jitter is 200 or 600 times what it should be, even though we try to optimize, it does not look reasonable to think that we're dividing the figures by a factor of 50 on average. So that's why we had to find a solution on userland. And then why not ODP, DPDK to handle that? Well, in the automotive industry, people have solved the problem for quite some time, and maybe they already have a TCP IP stack in userland and access the hardware through proprietary systems or proprietary methods. So why not having a standardized method that is valid for everyone, that is also consumable by DPDK, ODP, or even VPP directly? For example, one use case for VPP would be to have VETH access, direct VETH access for container networking, and be able to have a very high performance. So we wanted to have a very generic solution, okay? Now, zero copy. So why zero copy? If you look at the 100 gigabit adapter, that's 148 million packets per second. That's roughly 15 gigabytes per second, and that's roughly 1 DMA channel. So if you have the ring descriptors along with packets, plus what was just described as the virtual descriptors for an abstraction of that, and then you copy the packets. Basically, you have all the 4 channels of the CPU package that are fully used for that. So then for VPP, you have 0 memory bandwidth to look for the routes. And if you have 1 million routes, then you really have a problem. So for the design, we want to make sure that even for 100 gigabit, we still preserve memory bandwidth for the real application. Secure, so in the past, we've been using UIO or things like that, or VFIO, no MMU. And in the context of Spectre and Meltdown, I would say that we probably want to make sure that the memory is a very well protected subsystem. So let's not do any other way than IO-MMU. Userland network IO. So network IO is not about building a device driver. It's about just getting the packet queues and the packets themselves. Let's not initialize the hardware. If you look at the code size for a Realtek adapter, it's 10,000 lines of code, and out of those 10,000 lines of code, you may have 8,000 lines which are about the different initialization procedure for this particular flavor or this particular hardware revision. And you don't want to replicate that whole thing in DPDK, ODP, or VPP. So what you want is to let the kernel do what it's good at driving the devices, but let the userland capture just the data path. And if we want to have a dual stack, so that's which means that one port can be used by the kernel and a userland application. So the very idea is you have netdevs in the kernel that have rings and packets, and through some communication, what we want is to be able to have the rings accessible or visible in the userland, and the packets also controlled through userland. But what we want also is that if you use normal ifconfig or other IP route to commands, that they can influence the userland application. And if the userland application wants to change the MTU, it will just use the equivalent of the netlink interface or whatever IOCTL you need to change that. So that's where the design goes. One way to implement was just described. Use XDP, and that's a very good solution. Now, we have another topic, which is if you go really high speed on the network, what about storage? What about the other accelerators for crypto, compression, pattern matching? If you have a solution for network, but you don't have a solution for the other aspects of the life cycle of communications, then you may just solving a part of the problem. So we think we need a solution that addresses I/O in general from userland in a very generic way that can be applied to storage blocks, to crypto acceleration, to compression, etc. And also that is able to handle all the I/O models that you can find on Earth. And let's talk about the I/O models a little bit. So that's a typical NIC. So you have descriptors and you have packets. Usually everyone thinks of this model only. So you have a bunch of buffers, fixed size buffers, let's say 2 kilobytes, and that represents the packet memory. And then you have the descriptors, and before being able to receive packets, you have to state in each of those descriptors where are the different buffers. So that's the typical model. In that model, on a 2 megabyte huge page, you can squeeze 1,000 packets, 64 byte packets or 1,500 byte packets. You can squeeze only 1,000 packets. Now there are other methods which is common in ARM SoC's environment. You have those descriptors, but you may have multiple packet arrays. This is not about queues, where you have RSS, and when you want to distribute the load between different queues. That's a different topic here. This is about having, let's say, packet cells that are 128 bytes. You have packet cells of 256, and packet cells of 2 kilobytes. What this means is that you can have multiple packet arrays, and for a single flow, you can have multiple packet arrays, which means that if you're doing an IPsec offload in software or in hardware, for a single tunnel, you can have multiple packet queues. Well, sorry, multiple packet arrays that can be handled by different CPUs or different hardware blocks. So This, for example, in the IFXDP is not yet supported, but maybe that was the discussion on the mailing list. Maybe the model can be extended to support that. It's yet not fully known. There is another model for packet reception, and that's the tape model. So you have the descriptors. That's the only common thing in all those packet I/O stuff. And then you have an unstructured memory area. You have no notion of a packet buffer at all. So all packets are just put one after the other, or between, let's say, with some placement rules. But the hardware decides exactly where it wants to place the packets. So in that case, for example, for a 2 megabyte area, you can squeeze 32,000 64-byte packet, which is a little bit more than 1,000. So those models, why do they exist? This model is essentially to be able to have parallelism on a single tunnel. This one is to be able to beat the DMA transaction bottleneck that we have on PCI. On PCI, on the Gen 3 times 8, you have roughly 42 million DMA transactions per second, regardless of its ARM, Intel, or whatever. That's a PCI limitation, which means that if you have one packet equal one DMA transaction per second, your limit is 42 million packet per second. So if you have a 50 gig line card, which is in theory 74 million packet per second, if you use that model, you can't reach line rate. It's not because your software is not good. It's the fact that the DMA transaction limit the amount of I/O you can do. So that's why those models exist. For transmit, we have the same stuff, and you have ways to again to beat the DMA transaction limitation on the output side. So AF packet was good, but we need more than just networking, and we need to be able to to support all the I/O models. DMA-BUF has been around for quite some time, but it's well done for large buffers or even more than 4 kilobytes, but not for 64-byte packets and 148 million packets per second. If you use VFIO natively, you lose the netdev support in the kernel. So we thought that VFIO mdev, which has been introduced by Intel to support virtual GPUs in QEMU, was the right underlying framework to support userland I/O for not only networking, but also for other accelerators. And by the way, the VFIO mdev route is being investigated by Intel, which is Sunming Liang and Red Hat on one side, and Huawei is working on leveraging the same VFIO mdev for crypto device support. So one thing we ended up doing is we separate the packets and the rings. We say that the rings are the entities that are managed by the kernel. Creating a ring, creating a queue can be very complicated depending on the hardware. So we don't want the userland application to deal with that complexity. At the same time, also, when you transition from kernel to userland, you don't want to have an undefined ring. You may have an empty ring, but you don't want to have an undefined ring. So the idea was to keep the life cycle of the rings inside the kernel and just bring the packet memory handling into userland. And that's that's what happens for the life cycle of an application that use netmdev. So first of all, we want to make sure that there is a limited or zero difference from a code perspective when the netmdev is activated or not in the kernel. So if you have a FOSDEM driver, if you load it, it will behave exactly as if let's say the additions, the patches were not there. But if you have this global enable parameter, then there is a little bit of change in the code path. What the change do is essentially make sure that we don't create security issues. So we make sure that the rings are page size aligned and a number of things like that. Once the driver is loaded, we have to capture the queues in userland. So we do a set of configuration. Those configurations are coming directly from the Intel VFIO MDev framework to build virtual GPUs, but we use it to create virtual NICs. We ensure that the transition from kernel to userland happens in a very in a smooth way, and we leverage a very generic VFIO MDev framework to pass all the relevant structures to control the hardware. So the doorbells, the different, if it's a PCI device, the different config spaces, etc. So when the application starts, it's just using the VFIO MDev system call. So we have not defined that. That's already in kernel 4.10. We just make sure that we added some semantics into the framework that is about packet queues and packet arrays. And then the userland actually does the allocation of memory in a way that is consistent with the different I/O models we saw. And there is something that has to be done in this context. As we're dealing directly with the hardware, there is one thing which is a little bit complex, and that's DMA syncing. So in some architectures, DMA operations are always coherent, which means that you don't have to deal with cache validation or flushing in those architectures. But most architectures are not like that. And you need to deal with that. And so that means that at some point you may have to do what the kernel does, but in a smarter way so that we don't lose the performance by doing DMA syncs on every packet. You may want to do like VPP, you may want to do DMA syncs on a vector of packets. So what this means in terms of code, we tried that on a number of systems, and that's the kernel driver code base, and that's the kernel and userland lines that have been added to actually do packet I/O. If you look at the DPDK PMD for this, we're closer to 30,000 lines because it's replicating the same stuff. Well, here we're looking at a very reduced. Now, if we look at performance, so on this 40 gig card, on the transmit side, we reached the DMA transaction per second rate. On this one, we don't know if it's a hardware limit or if it's the way we actually handle the hardware. For this Chelsea card, we beat the DMA transaction per second because they have an I/O model that allows it. And we know that we don't know how to properly drive the hardware yet. And talking with the Chelsea guys, we know that for the T6 50 gig card, we'll be able to receive and transmit at line rate. But that's the goal for the next few weeks. Yes. So, what's next? I think I'm running. I'm good. We haven't yet pushed an RFC because we needed to make sure that at least it works. It was not clear, and we really would like to talk with the AFXDP guys. So hopefully we'll be able to talk with a beer later today. We don't really want to say that that's the way to do things. We'd like that the community finds a way that is acceptable so that we reach a certain performance level and a certain, let's say, genericity of architecture support, and also maybe go a little bit beyond the network. So this is really about discussion. Now, the kernel has no, that's a personal topic. Usually the kernel considers the hardware is good, that it drives it, and that's good. But what happened with the management engine and all those stuff, and the fact that GPUs have programs running on it, that network cards have programs running on it, you can't really trust the card to not do DMA on any area of memory. So I would like, we always consider that devices should always be now behind I/O MMUs, so that whatever happens inside the device, the firmware, the software, does not attack the kernel from outside. There is something else, which is the coherent interconnects. So you have C6, you have OpenCAPI, you have, Intel has, I don't know the name for that. I don't know if I should know the name for that, but anyways, those models will radically change how we should build device drivers. Because, for example, we always think that there is DMA, so we have a packet and we want to move that packet from the card to the host. But with coherent interconnects, you will just be able to pass a pointer and say that's the packet. And if you want to access just the header, you will just but you will bear the cost of the header, but there will be no transport of all the packet from the adapter to the host memory. Which means that typically we try to avoid scatter-gather list and have tail room and headroom to be able to add tunnel headers. But with C6 and coherent interconnects, that may be totally useless. So I think this will change the way we do drivers. And Gen Z is almost multiplying the memory bandwidth by a factor of 6 to 8. So this will also change how we'll see memory. And because of that, I would like those ideas to be integrated in the userland frameworks. And I'm done. So, any questions?
So, why do you create a bidirectional mapping of the packet arrays?
Why do I create a bidirectional mapping?
Yes. It was mentioned explicitly in your slide. I guess that's relevant.
You mean the ring descriptors? I don't see bidirectional. Sorry? In the middle. Ah, yes, bidirectional, yes. Because if you do a packet forward from port A to port B, when you first get the buffer, you don't know. Well, you want to be flexible in the way you will be syncing. So you can allocate the buffers as bidirectional and then do the mapping at the latest moment. But essentially what is important is that the IOMMU domain has to span all the IOVA has to span all the devices so that one IOVA address is valid for any descriptor that you will put into. I don't know if it makes good English.
For the packet buffers, or also for the descriptors?
Descriptors are different. They are, as they are maintained by the kernel, they are, they are not in a separate IOVA, but we can consider that they are in a separate IOVA on which we have a userland mapping. But we don't control the bus address of that because that's the kernel who decides. And when we map those areas from the userland, we never specify the DMA or the bus address. We just specify a VFIOMDEV region ID, which will be then translated so that we don't mess around with addresses from the kernel.
Okay, so we have no more time for questions, I'm afraid. So, Francois, thank you very much.
Thank you.